Hello, my name is Mia Rincones and I will be presenting the AP Stats project. I got Get Your Heart Beating project, which compares two different types of experiments, a completely randomized design and a matched pairs design. So what I first did was the materials that I had were a blood pressure machine. A pressure machine doesn't only track your blood pressure, but it also tracks your pulse, which is what I used it for. So I got a group of 30 people in total. Each person had to grab a slip, whether it said to sit or stand. And for that, I checked their heart pressure. Then I put it all into the data. So in this spreadsheet right here, you would see my data. So you would see that for the standing heart rate, the mean is actually greater than the sitting heart rate, as well as the median heart rate for standing is greater than the sitting heart rate for that as well. So essentially my main question was, is there some evidence that standing pulses are higher on average? Well, when you put it in a graph, you would actually see that on a dot plot, the sitting has a approximately normal graph with a possible outlier, as well as the standing heart rate dot plot is actually multimodal since there are three peaks and a possible outlier to the left of it. And when you see that, here's just another example of what you can do to actually look at the graphs. You could draw a line over it and see where your values actually stand. So at this point, once you have your 5-number summary for your different heart rates, the sitting and the standing, you would do your state, blend, do, and conclude. And for the state, you would be doing your mu1 minus mu2 since you're comparing standing minus sitting. So your mu1 would be standing, your mu2 would be sitting. And the null hypothesis would be that mu1 minus mu2 equals 0, and the alternative would be mu1 minus mu2 is greater than 0. Our plan, this is going to be a 2-sample t-test for mu1 minus mu2, your standing minus your sitting. And our conditions, this is a completely randomized design with 30 people either sitting or standing. Our 10% condition is checked out with 300 less than the total number of people who could have been checked for their heart rate or for their pulse. CLT is met. There is a the minimum amount of people who needed to be checked in order for it to be approximately normal. So as we see in our 5-number summary, our N for our first one, standing, would be 15. Our mean would be 78.93. That would be our X bar. And our standard deviation is 10.88. As well as our N2, which would be 15, our X bar 2, our mean 70.46, and our standard deviation would be 11.57. So we would put that into our test statistic. So that is our statistic minus parameter over the square root of our standard deviation over n. So what that looks like is this top equation right here, which would give us 2.06, and we find that our p-value, which we would put in the calculator, is going to be 0.0289. So once you would go in the calculator, you would find TCDF you would put your lower bound as 2.065 because you're looking for it to be greater. So your lower bound would be your test statistic, as well as your upper value would be infinity or 9999, and then your n would be 14 because that's for one sample. So we got our p-value, and what does that mean? That means that we reject the null hypothesis, and we have convincing evidence that standing pulse rates are higher on average. So that what does that mean in terms of just day-to-day life? Well, when you're standing, you have a higher pulse rate than when you're sitting down. You might feel calmer, you might feel at rest than when you're standing. That's really what it means in a real life situation in terms of grasping what the rejecting null hypothesis is and what we have convincing evidence for. So onto our matched pairs design. I randomly selected students to either sit or stand, and on the slip of paper that they randomly got from a box, it would say 1 sit, 2 stand, or it could say 1 stand, 2 sit, which means first, what would they do? Would they sit and then stand, or would they stand and then sit? So I did that, and we could see this is our graph distribution from our data. So let me actually pull that up. Our n is 30. I did want to keep this at approximately normal when we do the state plan do and conclude. And when we actually do the state plan do and conclude, we would do the mu of diff, because for each person, you're going to subtract the standing minus sitting value for the heart rate. So when you do the null hypothesis and the alternative hypothesis, it is actually going to be mu of diff equals 0 for the null hypothesis, and mu of diff is greater than 0 for the alternative hypothesis. And it would be the same thing if you were to draw it on a graph on your bell shape. You would find the p-value for that, and then it would be on the greater side, so on the right side. This is a one sample t-test because you're getting one single value. You're not getting two values. You got two values to find your mu of diff. Our conditions, again, random. This is completely random. Our 10%, we got 30 students, and times 10, that's less than the total people who I could have gotten to check the pulse. 30 equals 30 for CLT, and there are no strong skews, so it would be approximately normal. Onto that, our n is 30, and our mean, or our x bar, is 2.73, and our standard deviation is 21.63. When you look at it on a graph, it somewhat looks like a multi-model. So you do have multiple peaks. You have a total of 4 peaks, really with no strong skews or possible outliers. So we would say that although it is approximately normal for the numbers, we can actually see that it's approximately normal, and it would be a multi-model. And for that as well, we would do the test statistic. So it would be statistic minus parameter over the square root of standard deviation over n. So when we put that into the calculator, our equation, we would see that we would use our mean. So the 2.73 minus 0 since our parameter is 0, we're using the null hypothesis equal to 0. And we use our standard deviation and our n. Our n would be 30 since we did use all 30 students. Then we find, this is our test statistic, 3.21. And we put that into the calculator again. So once you do that, it would be the same TCDF. You put the lower bound as 3.215, since I stated before that we want it to be above 0. So that would be our lower bound. Our upper bound would be infinity or 9999, and our degree of freedom would be 39. Our p-value, what we got is 0.0015. And when we see that, we know that that would be less than our significance value. The significance value that we're using is 0.05, since there's no one significance value that we're actually told to use. So what would this mean? This would mean that we reject the null hypothesis and we have convincing evidence that the standing pulse rate is higher on average. So again, that is the same for the other problem as well. When your p-value is less than your significance value, you reject the null hypothesis and you have convincing evidence for your problem, for whatever you're looking for. So when we look, what does this actually mean? And I do have one last problem or question here that was given to me. Which design provides more convincing evidence that standing pulse rates are higher on average than sitting pulse rates? Well, when we compare the completely randomized design and the matched pairs design, we can actually see that the matched pairs design has a p-value that is much closer to 0, and it is much more less than the significance value. So the randomized design has a greater p-value than the matched pair design, which proves that the matched pair design has greater convincing evidence that standing pulse has a greater pulse on average. So looking on terms of what we see here, this is really what we're looking at. We're trying to see which one is actually more of a design that we would go for if we were to do it all around the world or with more people, and which one would provide accurate evidence, more convincing evidence that standing is greater of a heartbeat than sitting. So that's all I have for today. Thank you for watching. If you have any questions, please let me know. Thank you so much.